Show you a few examples of writing Lewis structures for third, fourth, and fifth period elements, which always involve a so-called, well, I shouldn't say always, but often involved a so-called expanded valence shell. In other words, having more than 8 electrons in the outer shell. The atom that has more than 8 electrons in the outer shell will always be the central atom. This is the way this always works out. For example, if you consider something such as, say, sulfur dioxide. And we're going to compare that with carbon dioxide just to show the importance of the difference that arises here. In both cases, well, in the case of sulfur dioxide, I would look at that structure and argue that oxygen for sure has to have a total of 8 valence electrons and should probably follow the usual rule that oxygen makes 2 bonds and has 2 sets of non-bonders. This is certainly true if you want to have a neutral oxygen atom. So I might start out by putting sulfur in the middle because it's the central atom, it's the single copy atom, and write 2 oxygens, 1 on each side, with 2 sets of non-bonders, and look at that structure. And then I have to ask the question, well, there's a sulfur that looks as though maybe it's obeying the octet, but if sulfur is to be neutral and obey the octet, it should make 2 bonds and have 2 sets of non-bonders, because after all, sulfur should feel a total of 6 electrons in its valence shell as far as its charge is concerned. And remember the rule here. The number it feels N is half the bonding electrons plus all the non-bonding. And so this sulfur feels a total of 8 bonding electrons, half of which is 4. It's short 2. It's a 6A element. It's supposed to be feeling 6. So far it only feels 4. So I have to give it another set of non-bonders. You can also rationalize this in terms of counting valence electrons. In other words, these are all 3 of these atoms are 6A elements. There should be a total of 3 times 6 is 18 valence electrons. And if you count them out, you'll only have 16 until you put the 2 up there on the sulfur. So there's an example of sulfur with 10 valence electrons, but it's a neutral sulfur, and that's what I was going to look for. On the other hand, with carbon dioxide, I would start out the same way and find myself with 2 double bonded oxygens and look at the carbon there, and that carbon has 4 bonds, but that's the correct structure for carbon. Carbon's supposed to have 4 bonds and have no non-bonders. And if I want to count N here, carbon has a total of 8 bonding electrons, half of which is 4. It's a 4A element, so it's neutral. So again, carbon, being a second period element, will never exceed the octet rule. Sulfur often does. Another example of this might be, for example, sulfur trioxide. Here, if I look at this structure, again, I'm going to follow this important rule because so many of these structures do have oxygen in them. Let's always satisfy oxygen's need for 2 bonds and 2 sets of non-bonders. That throws an automatic 6 bonds around that sulfur atom. However, that's a total of 12 bonding electrons. Half of 12 is 6. That's a neutral sulfur. But that's a sulfur that has a total of 12 electrons in its valence shell, far more than 8. Another good example of this kind of a situation arises with, for example, some of the polyatomic ions. And some good examples of that might be sulfate and sulfite. Again here, if I start out using my first rule, sulfur's in the middle, and oxygen must obey the octet rule. My second rule here is oxygen should carry the negative charge. I have 2 negative charges in both of those ions, and I should have those negative charges on oxygens. So I can start out in both cases by writing sulfur with 2 double bonded oxygens and hang 2 single bonded oxygens on the sulfur for sulfate, because after all, that gives me 2 negative charges, 1 on each of 2 oxygens. Each of these oxygens follows the usual rule here of having 2, 4, 6, 8 electrons in its valence shell, but 2, 4, 6 plus 1 of these bonders is 7, so that's a 6A element having 7 electrons in its feeling 7 electrons in its shell, so it's a -1. The other 2 oxygens, on the other hand, are typical oxygen atoms, 2 bonds, 2 sets of non-bonders. On the other hand, with a sulfite here, I can put 1 double bond O, because I need a neutral O, and therefore 2 sets of non-bonders to the double bond O, and then I get 3 sets of non-bonders around the other 2 oxygens, again giving me negative charges on both. However, In the sulfate, if I notice, this sulfur has 2, 4, 6, 8, 10, 12 bonding electrons, half of which is 6. That's a neutral sulfur atom. This sulfur over here on sulfite, on the other hand, sulfite, has 2, 4, 6, 8. Half of 8 is 4. It's lacking 2 electrons. And this is often what comes up in these situations. Always check your central atom. And if the charge isn't correct, you'll find you have to add one set of non-bonders to give you the sulfide ion. This is going to have a big influence on the shape of that molecule, and that's a topic that we look at later. Also, briefly reviewing the concept of resonance here, notice that there's no particular reason that the oxygens with a negative charge have to be the ones I have in these structures. One example, for example, I could draw a resonance structure for sulfite like this, where I have my double bonded oxygen on the right hand side of the structure. I could draw a resonance structure rather for the sulfate ion like this, and you can imagine there are others to draw here also for these two resonance structures that would look like this. All these things are possible. And these are just alternate structures, alternate drawings, really, of the true structure. What both of these resonance ideas are saying, here are just two examples for the sulfite, two examples for the sulfate, is that I can't draw a Lewis structure that adequately shows my molecule. I have to draw a series of structures. But what it also says is that, in truth, all 4 of the bonds in sulfate, all 3 of the bonds in sulfite are equivalent to one another. And for example, in sulfate, I have 4 O atoms with a total of 2 negative charges. So in truth, each oxygen is similar to one another, or equivalent, and each oxygen has a net 1/2 charge. In the sulfite, I have 3 atoms that are equivalent to one another. Each one has a net 2/3 charge. You can't show that in a Lewis structure, but that's simply the reality of the situation. A good example that also enforces the idea of looking at the non-bonding electrons is looking, for example, at the series perchlorate, chlorate, chlorite, and hypochlorite ions. Notice here that if I put a chlorine in the middle and hang 4 oxygens on my chlorine, and recognize that I have to have 1 negative charge, I just instinctually put non-bonding electrons around, double bonds around 3 of these oxygens to make them neutral, and leave the last oxygen negative. Again, they're resonance structures. I can draw any one of those 4 oxygen atoms with a negative charge. I immediately check out the charge on chlorine. This chlorine in perchlorate has 2, 4, 6, 8, 10, 12, 14 electrons, all involved in bonding. Half of 14 is 7. Chlorine is a 7A element. That's a neutral chlorine. When I go to chlorate, on the other hand, I draw the same idea. I've got 3 oxygens, so I have 2 of them double bonded, and again, 1 of them with a negative charge. Doesn't matter which one I show as a negative charge. And again, I've taken care of the oxygen issue. But when I look at the chlorine, I see 2, 4, 6, 8, 10 bonding electrons, half of which is 5. Chlorine is supposed to be neutral here. It needs 2 more, so I give it a set of non-bonders. Chlorite, on the other hand, when I hang 2 oxygens, 1 of which is double bonded on the chlorine, and again settle oxygen's needs first by giving it the negatively charged oxygen 3 sets of non-bonders, the other oxygen 2 sets of non-bonders. Then I look at the chlorine and see that so far I have a total of 6 bonding electrons, half of which is 3. I need 7, so I need 2 sets of non-bonders. On the other hand, with a hypochlorite ion, interestingly, if I bond a chlorine single bonded to an oxygen and give chlorine 3 sets of non-bonders, you really end up with a structure that's actually obeying the octet rule, despite, of course, the fact chlorine's in a 3rd period element. You know, you have analogous ions for bromine and iodine, perbromate, bromate, bromite, and hypobromite, but you don't have any of these for fluorine. And again, this reinforces the notion. Fluorine is a 2nd period element, and 2nd period elements never exceed the octet rule.